Okay, welcome back everyone. This is part 2 of the narrated PowerPoints for chapter 14, Continental Mountain Building. And what we're going to mostly do in this second part is to dive into the details of mountain building processes at both subduction zones and collision zones. So what you're looking at here is a way of dividing up a typical subduction zone. So beginning with the plate boundary, which is marked by the trench on the sea floor, right here. And then moving inboard towards the continent, we have a threefold designation, including the accretionary wedge, the four-arc basin, and the volcanic arc. Let's start with the accretionary wedge. What the accretionary wedge is simply material that was once part of the subducting oceanic plate. And that material in the process of subduction has been scraped off of the subducting plate and plastered onto the edge of the non-subducting plate. And in the process, that material becomes highly deformed and sheared and faulted and folded. It essentially becomes like geologic gobbledygook. So the material within the accretionary wedge represents all different rock types, including igneous, sedimentary, and metamorphic. And then from here, I'm actually going to jump over to the most inboard portion of the subduction zone. That is the portion closest to the middle of the continent. This is the volcanic arc. You're familiar with volcanic arcs already. And this is an area of intense igneous activity. So we get magmatism, the emplacement of liquid rock at depth, and we get volcanism at the surface. And these processes give rise to the volcanic arc, which is right here. So at depth, beneath the arc, we of course get intrusive igneous rock, and then at and very near the surface, we get volcanic rock in the volcanic arc. So the thing about both the accretionary wedge and the volcanic arc is that these tend to be topographically high areas. When enough time goes by, the accretionary wedge can actually be pushed up above sea level a little bit to form a sort of offshore island. And the volcanic arc is obviously an area of continental mountain building already. And as both of these areas are uplifted and eroded, they both contribute sediment to this low-lying basin in between. That's of course known as the four-arc basin, and the four-arc basin is in front of the arc and behind the accretionary wedge. It's kind of in the middle between those other two features. And in the four-arc basin, sedimentary rock dominates. So material builds up in the four-arc basin in relatively flat-lying layers of sediment from both the accretionary wedge and the volcanic arc. And these layers of sediment eventually become lithified to form sedimentary rock. And as shown in this diagram, at least at first, the sedimentary rock that's forming in the four-arc basin is marine sedimentary rock. Eventually, what can happen is the four-arc basin completely fills up, and in the later stages it's possible to get the deposition of non-marine sedimentary rock in the four-arc basin. And the take-home message, though, is that in contrast to the accretionary wedge, which is all rock types, it's geologic gobbledygook, it can be anything, and the volcanic arc, which is mostly igneous rock, the four-arc basin is mostly characterized by nicely layered, relatively undeformed sedimentary rocks. And let me say a little bit more about the various rock types that we find in these three areas. So there on the left-hand picture is an actual photograph of typical accretionary wedge material. It's known as mélange, which comes from the French word for mixture. And a good way to describe mélange, it's essentially a tectonic breccia. That just means It's a bunch of broken pieces of other rock that are all kind of mushed together and highly deformed as they're scraped off the downgoing subducting plate and accreted, that is, plastered onto the edge of the non-subducting continental plate. So again, we find all three rock types within the accretionary wedge: igneous rocks, sedimentary rocks, and even metamorphic rocks. And they're highly mixed together and deformed into this variable material, this mixture of many different rocks called melange. And then as we move inboard towards the center of the continent from the accretionary wedge to the four-arc basin, of course, we get first marine and ultimately non-marine sedimentary rocks forming in this low-lying area in between the accretionary wedge and the volcanic arc. And you can see in this center photograph, we're seeing nicely bedded, that is well layered sedimentary rocks. In this case, what we're actually looking at are marine sedimentary rocks formed from deposition associated with turbidity currents. And you might remember in a previous chapter that turbidity currents occur when sediment mixes with seawater and then it kind of roars down slope into the deeper ocean areas. They're essentially clouds of sediment, turbid water. And when those clouds come to rest on the sea floor, the rock becomes, and the sediments become nicely layered. And then when the sediments are lithified, they turn into turbidites. And so that's what that's the photograph that we're looking at in the Four-Arc Basin. And then as we continue to move inboard, we move into the continental volcanic arc. And this area is, of course, characterized mostly by igneous rock, extrusive igneous rock at the surface and intrusive igneous rock at depth. And as you also know from a previous chapter, the typical kind of volcano that we get at volcanic arc areas within a subduction zone would be a stratovolcano. And you might remember that stratovolcanoes are composed of alternating layers of lava and pyroclastic material, and they tend to be highly explosive. Okay, so that's a pretty good geologic summary of the three parts of a subduction zone: the accretionary wedge, the Four-Arc Basin, and the volcanic arc, and their associated rock types. Well, where was all this information developed? In other words, where in the world can we go to actually see this threefold designation in a subduction zone? And the answer is we don't really have to go very far, because this threefold model to help us understand subduction zones was developed in our own state of California, in the Central California area, so kind of in this area in California. And what we have in that area is once we cross over the transverse ranges and kind of move into the central portion of California, moving from west to east, we have three geographic regions: the California Coast Ranges, the Great Valley, and of course the mighty Sierra Nevada mountains. And so let's imagine a geologic cross-section stretching from A to A prime. And in effect, we're taking a slice through the earth, and then we're going to turn that slice and look at it sideways. That's what we're seeing in the left-hand diagram. So here's kind of a plate tectonic and a geologic cross-section moving from A to A prime in the ancient subduction zone that once occurred in Central California. So towards the southwest, we have, of course, the accretionary wedge. I'll just abbreviate that with AW. And you know about that already. Locally, the main deposits that we find in these ancient accretionary wedge rocks would be known as the Franciscan assemblage. They're so named because of really good exposures in the San Francisco Bay Area of accretionary wedge deposits. And then moving generally to the northeast, we then move into the Four-Arc Basin. I'll just abbreviate FAB for Four-Arc Basin. And geographically, we call that California's Great Valley. And of course, this is the breadbasket of California. It's one of the main agricultural regions in California. It's very flat and very monotonous. If you've ever driven I-5, Highway 5 from Southern California to, say, Sacramento or the Bay Area up in Northern California, you know how monotonous this area can be as you're driving along I-5 up through the Great Valley. If you look to the west, you of course see this set of low mountains. Those are those ancient accretionary wedge deposits from the ancient subduction zone. They're part of what we now call the California Coast Range. And then if you look to the east, on a clear day, as you're driving north on I-5, you can of course see the mighty snow-capped Sierra Nevada mountains. And of course, those represent the volcanic arc of the ancient subduction zone that was in this area during Mesozoic time. So that would be like the time of the dinosaurs. Okay, so that's sort of the main geologic model for helping us to understand the three different parts of a typical subduction zone. I now want to go into a little bit more detail with regard to how specifically material gets scraped off the subducting plate and kind of plastered onto the edge of the non-subducting continental plate. And just very briefly, let me kind of outline the continental plate. There's the continental plate right there. And then, of course, here's the subducting plate right here. So as the subducting plate dives underneath the continental plate, as we mentioned before, material gets scraped off of the sea floor. It gets scraped off the top of the oceanic plate, that's the subducting plate, and various materials that are embedded in that plate, as they're scraped off, they're then transferred to the non-subducting continental plate. And that process of transfer is called accretion. Accretion just refers to the lateral, that is sideways growth of a continent as a result of receiving that scraped off material from the subducting plate, which then gets added onto, or we would say accreted to, the non-subducting continental plate. And as far as the material that's being scraped off, very often we get big blocks, big crustal slivers of material that gets scraped off. And when we get one of those fault-bounded crustal blocks or crustal slivers that's getting scraped off the subducting plate, plastered onto the continental plate, we call it a terrane, T-E-R-R-A-N-E, as is shown here. In this case, we don't mean terrain in the sense that a geographer would use the term. We don't mean T-E-R-R-A-I-N. We're not talking about the lay of the land. We have a more specialized definition here. You can see the definition right there. A terrain in geologic terminology is, as I said, a sort of fault-bound block or a fault-bound sliver that represents material that's come from somewhere else and was rafted in this case, a subducting plate and plastered on to the edge of the non-subducting continental plate. So the thing to appreciate about terrains is that they're surrounded by faults, and I'll kind of illustrate that here. Let's look at this younger blue terrain. So I'll kind of add a thick black line here, and a thick black line here, and a thick black line here. So on all sides, except the upper side, of course, this block of material that once was part of the oceanic plate, maybe here, eventually got scraped off the oceanic plate and plastered onto the edge of the continental plate. So that so-called fault-bound block or sliver right there is what we call a terrane. And it's often the case that geoscientists refer to, quote, exotic terrains. Terrains are typically exotic in the sense that they've come from somewhere else and only more recently have they been plastered onto the edge of a continent. So they're exotic in the sense that they may have come from thousands of kilometers away, and they've been rafted into the subduction zone and onto the edge of the continent as a result of this kind of sideways, that is lateral continental growth that we call accretion. Okay, and I want to show you here just a quick video clip of terrain accretion. Here we go. Here comes the terrain being rafted in by the subducting plate, and bam, it gets plastered onto the edge of the continental plate during the accretion process. So let me show you that again. Here comes the terrain. And right there is when the terrain is accreted onto the edge of the continent. Notice that after terrain accretion, the continent is a little bit wider. It's extending a little bit more to the left than before terrain accretion. And it turns out that the edges of pretty much all of the world's continents are composed of a series of these fault-bound tectonic slivers that we call terrains. And we certainly see this in the Pacific Northwest along the edge of the North American plate. And you can see that before about 200 million years ago, literally the edge of the North American plate was right here. So this is the North American plate. I'll just abbreviate NA plate. Before 200 million years ago, that was the very edge of the North American plate. And then just within the last 200 million years or so, all of this material was plastered onto the edge of the North American plate such that it grew westward by hundreds of kilometers just in the last couple of 100 million years. And again, that process of continental growth is known as accretion. This is where terrains get accreted onto the edges of continents via subduction, and also it turns out as a result of transform motion as well in some cases. Okay, well, I want to change the subject a little bit now and just remind you of something that we've kind of implied up until now, but at this point I want to make it really explicit. And that is to say that collision always follows plate subduction in time. Another way of saying that is that plate subduction leads to plate collision. And here's how. In the left-hand diagram, you can see that we have a typical subduction zone. So we have an oceanic plate subducting beneath a continental plate. And as a result, the ocean basin in between the two plates progressively gets more and more narrow with time. And you can see that left-hand diagram, we've kind of picked things up in the very late stages of subduction. So we only have a really narrow ocean basin between the oceanic plate over here and the continental plate over here. And then as we fast forward in time a little bit, what literally happens is two different continents are then brought into direct contact. Here's a continent. Here's a continent, and with the closure of the oceanic basin in between, then the two continents become joined within a collision zone. So we have a continental plate here, and we have a continental plate here, and where they meet, we have plate convergence, but not plate subduction. And that's just another way of describing continent-continent convergence that we refer to as plate collision. So that's important to realize, that collision zones always develop from subduction zones. If you have a subduction zone anywhere in the world that contains at least part of a continental plate, then eventually the continental plate gets brought into and accretes onto the edge of another continental plate as a result of plate collision. And in general, the rocks become more and more deformed, meaning more and more faulted and folded the closer that we get to the middle of the collision zone in this case. And up near the surface, within the upper few kilometers of the Earth's surface in our collisional mountain range, faulting tends to dominate, meaning the rocks are breaking and cracking and moving differentially with respect to one another. That's because the rock is cold and it's not under very much pressure. In other words, the rock is behaving more as a brittle solid under low temperature, low pressure conditions. Deeper down within the collision zone at metamorphic depths, at depths of more than a few kilometers, it's not so much faulting that dominates anymore, but folding and metamorphism. And this is simply because when you go deeper and deeper within the collision zone, the rocks get warmer and they also become more plastic and more malleable. And so rather than breaking, the rocks do a lot of bending and folding, even as they're being transformed in the solid state during metamorphism. Let's do a quick concept check here. So there on the left, you're looking at a typical cross-section of a collision zone, so a continent-continent area of plate convergence. And the question then is, why do folding and metamorphism typically occur at great depth within a collision zone? So I'll let you think about that for 10 or 15 seconds and see if you can pick the right answer. All right, what'd you come up with? Hopefully you got the right answer. It's A. Folding and metamorphism dominate at depth because the rocks down there are warmer and under higher pressure, and as a result, they're more plastic. And if you think about it, when you go deep below Earth's surface, you get higher pressures and higher temperatures. Those are, of course, the exact conditions that you need for metamorphism. So it really is no surprise that we tend to see folding and metamorphism at depth versus faulting at the surface within a collision zone. Because again, at the surface, the rocks in a collision zone are relatively cold and brittle, and so they break along faults, whereas at depth, the rocks are warmer and under higher pressures, and those are the conditions required for both folding and metamorphism. Let's try another concept check. What type of fault is highlighted in the diagram? I'll give you 10 seconds or so to decide. By the way, a hint here is we're obviously looking at a cross-sectional diagram, we're not looking at things in map view. Okay, what'd you come up with? Hopefully you said A, reverse faulting. You might remember from the chapter on geologic structures that a reverse fault occurs when the head wall moves up relative to the footwall. And that's what's happening in the area that I've highlighted here. And you might also remember that reverse faults form as a result of regional compressive tectonic stress. So if the rocks in an area are being squeezed together in compression horizontally, reverse faults will be the result. And remember that a reverse fault is simply a type of dip-slip fault. So the motion along the fault is parallel to the dip of the fault plane. And for it to be a reverse fault, the head wall has to move up relative to the footwall. Okay, let's try another concept check question. we're looking at a collision zone again in cross-section over on the left. And the question is this: just before this collision zone developed, what type of plate boundary existed in this area? Well, hopefully that's an easy one. And I actually gave you a hint on this question because I left in a little reminder there that subduction leads to collision. And so in this case, the answer is that before the current collision zone existed in this area, we had a subduction zone. So before this happened, we had this going on. And then with the closure of that ocean basin, the subduction zone transformed into the collision zone. So the take-home message here is that collision always follows subduction. Okay, well, one thing that's interesting about collision zones in particular is that they tend to be complex and wide and kind of mushy. And a really good illustration of that is the collision zone that developed on the order of 40 or 50 million years ago as the Indian subcontinent crashed into southern Eurasia. And in this case, the two plates involved are the India-Australia plate. It turns out, depending on your perspective, both India and Australia are two continents embedded within the same plate, and that plate's sometimes called the India-Australia plate. So in this case, the India-Australia plate is generally kind of moving northward with respect to the Eurasian plate. And as I said, on the order of 40 or 50 million years ago, the subcontinent of India, which is a continental landmass, it's part of a continental plate, it crashed into southern Eurasia, which is also a continental plate, and a collision zone developed in this area. But what's interesting about the collision zone is you can see from the faulting patterns that it's really wide and kind of diffuse and incredibly complex. In other words, we can't really describe the collisional plate boundary here by just drawing one simple line on a map. And I'll kind of highlight here, but you can kind of see in the area all around the plate boundary and extending hundreds of kilometers kind of inboard from the plate boundary, we get lots of faulting. The actual plate boundary is shown in red. So if we did have to actually draw in the plate boundary, that would be the best approximation of the plate boundary. But the point is that a lot of this deformation and uplift and mountain building, it's not just confined to the area of the plate boundary itself. It actually extends hundreds of kilometers inboard from the plate boundary. So that's a really important characteristic of most collision zones. They tend to be wide and mushy. The deformation, the faulting, the uplift, the mountain building can extend for hundreds and hundreds of kilometers on either side of the actual plate boundary. And then the other thing that's fascinating about this area is that it's breaking up into smaller tectonic blocks that are being shoved eastward and having to get out of the way to accommodate the northward march of India. So notice that, here's India moving northward, and it's crashing into southern Asia up here. And as a result, all of these blocks of material, these kind of fault-bounded blocks, are having to sort of get shoved out of the way to the southeast to accommodate the continued northward march of India. So that's just another example of how complex collision zones can be. Mountain building processes and faulting and folding and all of that, they're not just confined to the actual plate boundary. They occur within this kind of wide mush zone, even hundreds of kilometers inboard from the plate boundary in this case. So next to these two diagrams, I'm showing the results of a research study that was done a number of years ago, where the researchers attempted to build a physical, actual model of this process in the laboratory. And you can see that over here. And what they did is they used two different materials to represent India and Eurasia. In this case, the wooden block right here represents India, and then the kind of striped material, I think it was a type of plastic, represents Eurasia. And what's interesting is that if when the researchers assumed that the India block was stronger than the Eurasia block, when they smushed India into Eurasia, it was the Eurasian block that suffered more deformation. And as I kind of alluded to a few minutes ago, what happens is the Eurasian plate here is kind of breaking up into a series of fault-bound blocks that are having to kind of scooch out of the way to make room for India as it smashes into southern Eurasia. So it was a really interesting paper in the sense that the researchers were able to not just create a mathematical computer model of this process, but an actual physical model in the laboratory that approximates reality pretty closely. You can see that the pattern of faulting in the model, in the blocks, it fairly closely resembles the pattern of faulting and block movement in the real world in Southeast Asia. So yeah, pretty interesting study. And since that study, researchers have referred to this process as, quote, watermelon seed tectonics. It's kind of a very colorful name there. But the idea is kind of like when you smush a watermelon seed, a wet, slippery watermelon seed, between your thumb and fingers. If you squeeze the watermelon seed really hard, the watermelon seed will shoot out of your fingers in the same way that as India and southern Eurasia are being squeezed together, Southeast Asia is acting like the watermelon seed. It's getting shot sideways out of the plate boundary area or really as a result of this compressional stress here. So yeah, all this is to say that continental collision zones can be quite complex, and they can be really wide and mushy when you get right down to it. Okay. What we now want to do in the last part of this presentation is to consider these different processes, subduction, collision, and accretion, on much longer geologic timescales, not just of millions or tens or hundreds of millions of years, but literally on timescales of billions of years. And when we when Mother Nature carries out these processes on timescales of billions of years, in a nutshell, this is how entire continents get made. And an interesting way to think about our own continent of North America is that it really is a collage, if you will, of various origins of different ages. And again, an origin here is just a continental mountain belt, as well as accreted terrains. And typically, these accreted terrains are subunits of a single origin. So you might have dozens of accreted terrains within one single mountain belt. That is to say that a single origin can be made up of dozens of accreted terrains. And just like we talked about earlier, given the way that the accretion process happens, in general, we find that the oldest continental mountain belts are in the interior of a continent, and the ages of the mountain belts and the terrains becomes progressively younger as you move from the middle of a continent, the interior of the continent out to the edges of the continent. And so here's sort of a simple model to help you appreciate what's going on here. If we imagine an onion, then each layer of the onion would represent an origin, a continental mountain belt. And so in the middle of the onion, we would have older origins. And again, each origin is probably going to be composed of dozens of accreted terrains. And then out towards the edges of the onion, we have younger origins. So this sort of onion-like growth of accreted terrains and origins is sort of a good conceptual model to help us understand how continents can get made over geologic timescales. And by the way, these ancient origins are pretty well mapped on the world's continents, and to keep track of them, researchers actually give them names. And so you can see over there on the right hand figure, each of the colors has a sort of unique name that represents an origin of a given age, that is an ancient continental mountain belt of a certain age. So here in kind of the center of the North American continent, we have the Superior origin. Out toward the edge, we have the Cordillera origin, the Wichita origin, the Appalachian origin, and so on and so forth. And in a sense, we're really looking at an amalgamation of pieces of many different continental plates of various ages. And this sort of collage or amalgamation of origins and accreted terrains led some researchers in one paper I read to refer to North America as, quote, the United Plates of America, sort of a play on the idea of the United States of America. But that's pretty cool, right? On geologic timescales of billions of years, the take-home message of this slide is just to appreciate that as a result of subduction, collision, and accretion, entire continents get made in this fashion over long stretches of geologic time. Okay, let's do a quick concept check here. So back to that map of origins of different ages. And again, each name and each color represents an origin, that is an ancient mountain belt or a not so ancient mountain belt of a given age. So the question then is, which origin has the youngest accretion age of the three possibilities, including the Superior, Wyoming, and Cordillera origins? So let's see, to help you see them, there's the Superior origin, there's the Wyoming origin, and there's the Cordillera origin. So based on that rule that we developed earlier, which origin has the youngest accretion age? I'll let you think about that for a little while. All right, hopefully you know the answer. So what do you think? Which of these three origins has the youngest accretion age? Well, it's the Cordillera origin. And by the way, you and I here in San Diego, or frankly, if you're, west of the Rocky Mountains and even within the Rocky Mountains, you're in the Cordillera origin. It's a massive continental mountain belt that formed within the last couple of 100 million years along the western edge of the North American continent. So between the Superior, Wyoming, and Cordillera origins, just from their relative positions, we know that the Cordillera origin would have the youngest accretion age. It's composed of material that was most recently laterally smushed onto the growing edge of the North American continent. We know that because the Cordillera origin is closest to the edge of the continent. That's how we know it has the youngest accretion age. Okay, well, we're almost done with this presentation, and I just want to mention in passing that now that we understand the way that mountain belts get made, and how do they get made? Three processes: subduction, collision, and accretion. Those are the three plate tectonic processes responsible for the growth of continental mountain belts. And ultimately, we have plate tectonic theory to thank for helping us to understand this. But I just want to quickly remind you that the different kinds of plate boundary are related in a temporal, that is time-related way. And what I'm showing you here is a kind of simplified diagram known as the plate tectonic cycle. And the only message here is simply that one type of plate boundary will always come after the other type in a constant cycle that never ends. So let's pick things up at step one, and at this point we have continental plate divergence. That's known as rifting, when a large supercontinent like Pangaea breaks up into smaller pieces along a series of continental divergent plate boundaries. We call that process rifting. So approximately 200 million years ago, the Pangaean supercontinent rifted apart along a series of divergent plate boundaries. That's step one. And step two is just a continuation of that divergence process. And pretty soon, the supercontinent breaks up into two or more separate pieces. And at that point, we have step two. We now have oceanic plate divergence. So in step one, we're not yet forming new oceanic lithosphere. In step two, we are, but we still have a divergent plate boundary in step two. These two plates are moving away from one another. In steps 3 and 4, there's step 3, there's step 4, subduction now begins. So an ocean basin, as plate divergence proceeds, as you know by now, gets wider and wider and wider the more we pull the two plates apart on either side of the ocean basin. But that process, as you maybe suspect, can't continue indefinitely. Eventually, an ocean basin has to stop widening because the Earth is a finite size, and eventually the ocean basin will start closing up again along one or more subduction zones. And that's what's happening in steps 3 and 4. Is plate divergence has ended, and plate subduction is now closing up the ocean basin that was earlier created as a result of plate divergence. And eventually, in step 5, two continents meet to form a collision zone. And indeed, this is how supercontinents are put together. And you kind of know this by now as a result of, well, subduction, but also continental collision. Small continents get mushed together into a collage, forming a much larger continent called a supercontinent. And then the very last stage here in the plate tectonic cycle is that supercontinent then just erodes for a while, and eventually the cycle is complete and the process starts all over again. So you don't really need to worry about memorizing this entire diagram. I just want you to appreciate that subduction and collision, and indeed, if you will, the plate tectonic cycle occur because these different processes are all related to one another in time. Okay, and I'll just end with a quick view of what you need to know in terms of summarizing the information in this, well, really the last two presentations. I'll include the same information on the study guide. Okay, thanks everyone.